Hey everyone, welcome back to Chem Story. Today, we're going to look at another key reaction that alcohols can go through, elimination. We'll see how alcohols are turned into alkenes, and we'll break down the mechanism one step at a time. By the end of this lesson, you'll clearly understand how elimination works, what kind of conditions are required, and how the structure of the alcohol influences the outcome. All right, let's jump in. Let's start with the most common elimination reaction of alcohols, dehydration. When you heat an alcohol with acid, it loses water and forms a double bond. Here's what's happening. The OH on the alpha carbon and a hydrogen on the beta carbon are both taken out. As they go, a new pi bond forms between those two carbons, giving you an alkene and water. It's called dehydration because we're literally removing water from the molecule. Pretty straightforward and elegant. Now here's the thing. The OH group isn't a good leaving group. Hydroxide is a strong base, so it doesn't leave on its own. To make elimination work, we need to turn it into something better. One way is to add a protic acid, like sulfuric acid, that turns the OH into water, which is much easier to kick out. Another way is to use POCl₃ with pyridine. It makes the leaving group much better, even under mild conditions. Or you can convert the alcohol into an alkyl sulfonate, like a tosylate or mesylate. Both work great in elimination. Once that conversion is done, the reaction goes much more smoothly. All right, let's start with the first method for eliminating alcohols, using a protic acid. Here's how it works. You take an alcohol and add a strong acid, like sulfuric acid or phosphoric acid. With heat, the acid protonates the OH group, turning it into water, which is a much better leaving group. Once that happens, the molecule goes through elimination, and you end up with an alkene. And since you're removing an H and an OH from neighboring carbons, you also get a molecule of water. This process is actually reversible. Under acidic conditions, you can go the other way and hydrate the alkene to get the alcohol back. Now, here's something important to keep in mind. This reaction is in equilibrium. You can go from alcohol to alkene, which is dehydration, but you can also go the other way, from alkene back to alcohol through hydration. So how do we push the reaction toward alkene formation? According to Le Chatelier's principle, we need to remove the water that's produced. By getting rid of it, we shift the equilibrium to the right, favoring the alkene. So controlling water is key if you want a good yield. So how do we actually remove water during the reaction? There are two common ways chemists do this. One is using a Dean-Stark apparatus. It physically pulls water out as it forms and collects it in a separate trap, keeping it out of the reaction. Another option is using a desiccant, which is a drying agent that absorbs water. Things like molecular sieves or salts like magnesium sulfate or sodium sulfate work great for this. Using either method helps shift the equilibrium toward the alkene, making the elimination more efficient. Now let's talk about how elimination works for different types of alcohols. Secondary and tertiary alcohols usually follow an E1 mechanism, where a carbocation ion forms, and that's pretty stable, especially with tertiary carbons. These reactions happen under mild conditions, so you don't need high heat. They typically give the Zaitsev product, meaning the double bond forms at the more substituted, more stable position. But since a carbocation is involved, rearrangement can happen if there's a chance to form something even more stable, so always keep that in mind when predicting the product. Let's go through a classic example. We're starting with a tertiary alcohol, and under acidic conditions, the OH group gets protonated and leaves as water. That forms a carbocation ion on the central carbon. Next, a beta hydrogen is removed, and depending on which one goes, you can get different alkenes. Here, the more substituted alkene is the major product because it's more stable. That's the Zaitsev product. The less substituted one shows up as the minor product. This is a textbook example of the E1 mechanism, stepwise, with possible rearrangements and product ratios based on alkene stability. What about primary alcohols? They don't form stable carbocation ions, so E1 doesn't work. Instead, elimination goes through an E2 mechanism, a single-step reaction. But it usually needs very high heat, which makes it hard to use in the lab. If the conditions are milder, you're more likely to get substitution, often forming ethers instead. So overall, acid-catalyzed elimination isn't the best choice for primary alcohols. Here's how elimination works for a primary alcohol under strong acid. The OH group gets protonated by sulfuric acid, turning into water, which is a much better leaving group. But since primary carbocation ions aren't stable, the reaction takes the E2 pathway instead. The beta hydrogen is removed as the leaving group exits, all in one concerted step. That gives you an alkene and water. Just keep in mind, it needs high heat and isn't very efficient. Now let's look at a much more practical method, reacting alcohols with POCl₃ and pyridine. This works well for primary, secondary, and tertiary alcohols. Instead of using strong acid or high heat, it offers a milder and more selective way to do elimination. It follows an E2 mechanism, so there's no carbocation ion and no rearrangement, which is a big advantage. Overall, it's a cleaner and more reliable method, especially when you want to avoid the issues that come with acidic conditions. Let's break down how POCl₃ pyridine elimination works. First, the alcohol reacts with POCl₃. The oxygen attacks the phosphorus, and a chloride ion gets kicked out. This forms an intermediate with a POCl₂ group, which is a great leaving group. Then, pyridine removes a proton from the oxygen to neutralize it. Now the molecule is ready for elimination. Another pyridine takes a beta hydrogen, while the OPOCl₂ group leaves all in one concerted step. That's your classic E2 mechanism. No carbocation ion, no rearrangement, and the result is a clean, high-yield alkene. The third method is to convert the alcohol into an alkyl sulfonate, like a tosylate. This method is widely used because sulfonates are great leaving groups, which makes elimination much easier. Once the conversion is done, the reaction follows an E2 mechanism, a one-step process. You get high yields and barely any side reactions. A strong base comes in, grabs a beta hydrogen, and at the same time, the sulfonate leaves. Let's take a look at the mechanism. We're starting with cyclohexanol. First, we treat it with TSCl, that's tosyl chloride, and pyridine. This turns the OH group into a tosylate, shown here as OTS, a great leaving group. Next, we add a strong base like tert butoxide. The base removes a beta hydrogen, and at the same time, the tosylate group leaves. That's your classic E2 reaction. Both steps happen together in one smooth motion, giving you the final alkene. Clean, efficient, and very predictable. And that wraps up our lesson on alcohol elimination. We've covered three major strategies: acid-catalyzed dehydration, POCl₃ with pyridine, and sulfonate formation, each with its own strengths and ideal use. Once you understand how each one works, you'll be able to choose the right method based on your starting alcohol and the product you need. Thanks for watching, and I'll see you in the next Chem Story video.